March 1943, Grand Blanc, Michigan. Another Sherman turret hits the factory floor with a sickening thud. The foreman doesn't even need to check the measurements anymore. He can tell just by looking that this one won't fit its hull either. That makes 3 this morning, 3 expensive pieces of carefully welded armor that might as well be scrap metal. The workers have a name for these problem turrets. Fighters, because they fight their hulls like prize fighters in a ring. The rejection tag tells the story in cold numbers. Gap measurement on the north side, 0.018 inches, south side, 0.031 inches. The Army specification allows 0.004 inches maximum. This turret isn't close to acceptable, not even in the ballpark. Plant Superintendent James Morrison watches another crane lower another turret, watches it hang up on one side, watches the gap on the other side open wide enough to fit 2 wrenches. He's been watching this same scene repeat for months now. 6 months ago, this building was making Buick engines for cars that Americans would drive to church on Sunday. Today, it's supposed to pump out 48 Sherman tank turrets every single day for a war that's eating tanks like candy. The transformation happened fast, maybe too fast. Nobody at Fisher Body really knew how to build tank turrets when they started. They just knew they had to learn immediately. Here's the crisis that keeps Morrison awake at night. 1 in 8 turrets gets rejected outright. The reject rate is 12.3% this week, and it's climbing steadily. Each failed turret needs 4 men working 6 to 14 hours with files and grinding wheels. Even after all that labor, 30% get rejected again. The rework backlog is growing like a tumor. Then the telegram arrived from Washington, changing everything. The War Department needs Fisher Body to triple production immediately. Not gradually, not eventually, right now. From 720 turrets monthly to 2,160 monthly. Morrison read that telegram 4 times, hoping he'd misunderstood the numbers. He hadn't misunderstood anything. The math makes his head hurt when he works it out. Tripling production while rejecting 12% doesn't triple your rejects like you'd think. It actually quintuples them because quality control collapses under pressure. Fisher Body number 2 is staring at 260 rejected turrets monthly, based on current trends. That's 2,600 man-hours monthly, spent fixing mistakes instead of building new tanks. The War Department doesn't care about your problems, they just want tanks in North Africa yesterday. Every possible solution has been tried already. 3 additional quality control inspectors hired. A dedicated turret rescue team created from the best welders. An engineer flew in from Rock Island Arsenal, who measured everything with precision gauges for 2 weeks. His 23-page report basically said, "Your tolerances are too tight for mass production, but we can't loosen them or the turret won't rotate in combat." Real helpful advice that solved absolutely nothing. 10 other factories across America are fighting this exact same battle right now. Chrysler's Detroit Tank Arsenal, Pressed Steel Car Company in Pennsylvania, Pacific Car and Foundry in Washington State. They're all welding turrets and watching those turrets fight their hulls. The Army Ordnance Department scheduled a conference for April where plant managers can gather and share their collective misery. Meanwhile, every Sherman that doesn't roll off the line is a Sherman that won't be in Sicily. Worse, it won't be there when the inevitable happens and the Allies cross the Channel into France. Everyone knows that invasion is coming eventually. Nobody knows exactly when, but everyone knows it will require more tanks than America has ever built in history. Morrison walks past another tagged turret that made it to final inspection before someone caught the problem. The measurements are recorded in neat handwriting that somehow makes the failure worse. He checks his watch with growing dread. The morning production meeting starts in 12 minutes. He still doesn't have any answers worth sharing with upper management, who expect miracles. The scale of what America is attempting has never been done before in human history. 11 separate factories spread across 8 states, all building the identical tank to the same specifications. Detroit Tank Arsenal in Michigan, Lima Locomotive Works in Ohio, Pressed Steel Car in Pennsylvania, Federal Machine and Welder in Ohio, Pacific Car and Foundry in Washington, American Locomotive in New York, Baldwin Locomotive in Pennsylvania, Pullman Standard in Illinois, Montreal Locomotive Works in Canada, and the Fisher Body plants in Michigan. By June 1943, these facilities are collectively producing just over 2,000 Sherman tanks every single month. That's roughly 67 tanks per day. Somewhere in America, every 22 minutes a Sherman rolls out a factory door. But the production numbers don't show the nightmare happening inside those factories. Each Sherman turret requires 47 separate welds, not small tack welds either. Full penetration welds that have to be ground smooth, inspected with X-rays, and certified. The turret ring itself demands tolerances of 0.004 inches, thinner than a human hair. You're building to microscopic tolerances using equipment designed for railroad cars. The turret assembly process starts with the turret basket, the rotating floor where gunner and commander stand during combat. This basket must be perfectly circular because it spins on ball bearings. 126 individual bearings, each manufactured to within 0.002 inches precision. If the basket is even slightly oval, and welding heat makes metal move, those bearings will bind. A binding turret in combat means a dead crew trapped inside. Next come the turret walls made of rolled armor plate welded to the basket. 5 separate pieces, front, 2 sides, rear and roof. Each weld generates enough heat to distort the metal in unpredictable ways. Professional welders understand this instinctively. You weld one side, the metal shrinks as it cools, pulling everything slightly out of true. You compensate by welding the opposite side next, hoping to balance forces. But you never quite get back to perfect after that initial distortion. By the time you've completed all 47 welds, you've got accumulated distortion that's impossible to predict precisely. The turret ring itself gets bolted and welded to the bottom of the turret basket last. This ring must be perfectly flat within 0.004 inches across its entire 69-inch diameter. Achieving this with heat-distorted metal underneath is like balancing a dinner plate on crumpled paper. Then there's the supplier problem that nobody wants to discuss publicly. The Army specified 3 approved steel suppliers for armor plate production: Carnegie Steel, Republic Steel, and Inland Steel. All 3 companies produce steel that meets hardness and tensile strength specifications perfectly. But steel isn't perfectly uniform between batches or suppliers. One batch might have slightly different carbon content than another batch from the same mill. Different carbon content means different thermal expansion rates during welding operations, which means 3 identical turrets welded identically using steel from 3 different suppliers end up with 3 different final dimensions. The hand-filing solution that plants relied on since production began worked fine at 30 tanks monthly. You'd lower the turret onto the hull, see where it hung up, spend an afternoon with files and grinding wheels, time-consuming but manageable at small scale. At 2,000 tanks monthly with reject rates climbing toward 15% at some facilities, hand-filing became mathematically impossible. You couldn't hire file wielders fast enough even if you wanted to. The skilled workers simply didn't exist in sufficient numbers. Even if they did exist, every hour spent fixing a rejected turret was an hour not spent building the next one in the production queue. Fisher Body number 2 calculated that their rework backlog, if left unaddressed, would require adding 42 workers just to handle rejected turrets. 42 workers they didn't have, working on tanks that should have been built correctly the first time. Something fundamental had to change in the process. The question was, what and who would figure it out? Walter Kowalski clocked in for 3rd shift at Chrysler's Detroit Tank Arsenal on July 8, 1943, same as always, just like he had every night for the past 14 months without missing a shift. 3rd shift started at 11 p.m. and ran until 7 a.m., the shift nobody wanted. The shift where the cafeteria served yesterday's coffee reheated and day-old sandwiches because management figured 3rd shift didn't deserve fresh food like the day workers. Kowalski was a jig builder, Not a glamorous job that anyone talked about at parties. While welders and machinists got the spotlight, their work visible on every tank, jig builders made the fixtures that held parts during assembly. The invisible scaffolding behind the scaffolding. If a welder needed 2 pieces of armor at a precise angle, Kowalski built the jig that held them there. When the weld was done, the jig got unbolted and used again. He was 41 years old, which made him ancient by factory floor standards, where most workers were kids. Most of the workers were in their 20s, fresh from farms, or straight out of high school. Kowalski had been a commercial welder in Detroit for 19 years before the tank arsenal opened. He'd welded ship components, bridge sections, industrial boilers, anything that needed metal stuck to other metal at high temperature under pressure. When Chrysler converted their facility from half-track production to full Sherman production, they hired him as a jig builder rather than welder. The reasoning was simple. Welders were scarce but trainable. Jig builders were scarcer. And Kowalski understood how metal behaved under heat stress from nearly 2 decades of experience. What Chrysler hadn't counted on was that Kowalski also had opinions about how things should be done. Lots of opinions. In his first year at the arsenal, he'd submitted 8 separate improvement suggestions through official channels. Chrysler had a suggestion box system complete with printed forms and a review committee that met monthly. The committee consisted of 3 engineers and 2 production supervisors, who reviewed worker suggestions. They had rejected all 8 of Kowalski's ideas without implementing a single one. Suggestion 1. Modify the welding sequence on transmission housing to reduce distortion. Rejected. Reason stated: current sequence established by engineering standards. Suggestion 2. Redesign the jig for bow gunner's hatch to allow for thermal expansion. Rejected. Reason: design meets current specifications. Suggestions 3 through 8. Various proposals for fixture improvements, weld sequence changes, assembly process modifications. All rejected with reasons ranging from insufficient engineering justification to the insulting outside scope of submitters' expertise. By July 1943, Kowalski had stopped filling out those suggestion forms entirely. What was the point anymore? The engineers had their drawings approved by committees. The supervisors had their production schedules handed down from above. A third-shift jig builder with a high school diploma wasn't going to change anyone's mind with a piece of paper. But he still watched the production line, and he still noticed things others missed. He noticed the turret ring alignment problem getting worse, not better, despite all efforts. He noticed the growing stack of rejected turrets in the rework area. He noticed welders getting frustrated, filing down perfectly good welds, trying to force components to fit through sheer determination. He noticed everyone treating this as a welding problem or machining problem or steel quality problem. Nobody was treating it as a fixturing problem that could be solved with better jigs. Kowalski had developed a theory over 19 years of welding experience. He understood something the engineers with their drawing boards didn't grasp. Metal moves when heated. You can't stop it. You can't force it to stay perfectly still while pumping thousands of degrees into it. But what you can do, what a good jig does, is guide that movement, control it, work with the metal instead of fighting against it like the current jigs did. The turret alignment jigs currently in use were completely rigid by design. Bolt the turret ring into position, weld it, unbolt the jig, hope for the best. Rigid fixtures made perfect sense for parts that didn't distort much. For parts with 47 welds and massive heat input, rigid fixtures were fighting a losing battle against physics. Kowalski had been sketching an alternative design in a notebook he kept in his toolbox, not for any official purpose, just thinking on paper during breaks. The sketch showed something radically different, something that seemed crazy enough it might actually work. He looked at the stack of rejected turrets growing taller, then back at his notebook. Maybe just one more suggestion, even though the previous 8 got rejected. Maybe this time would be different. To understand why Kowalski's colleagues thought his idea was completely crazy, You need to understand what was happening inside those turrets during fabrication. The problem wasn't simple like a loose bolt. It was a cascading failure of physics, metallurgy, and manufacturing reality colliding head-on with engineering theory developed in classrooms. Start with the heat that welding generates. A typical welding arc operates at around 6,500 degrees Fahrenheit at the point of contact. You're essentially creating a tiny sun where two pieces of metal meet. The metal doesn't just melt at that point of extreme heat, it expands significantly. Steel expands about 0.00000 inches per inch of length for every degree of temperature increase. As the weld cools afterward, it contracts back down. But it doesn't contract uniformly across the entire piece. The area right next to the weld cools faster than the area 6 inches away, creating internal stresses. These stresses pull the entire structure slightly out of shape in unpredictable directions. Now multiply that effect by 47 separate welds in different locations, each one adding its own distortion, each one pulling the metal in a slightly different direction with different force. By the time the last weld cooled, the turret basket that started as a perfect circle had been pulled into something more like a polygon, with very gentle sides. Not enough to see with your naked eye, plenty enough to measure with precision gauges. Then you had the tolerance stack-up problem that engineers learned about in school. Engineering drawings specified tolerances for each individual component separately. The turret basket plus or minus 0.005 inches. The side plates plus or minus 0.004 inches. The turret ring mounting surface plus or minus 0.003 inches, maximum variation. Sounds precise and carefully controlled, right? Here's the catch that makes it fail. Those tolerances add up across assemblies. In the worst-case scenario, if every single component was at the loose end of its tolerance range, and all those tolerances stacked in the same direction by chance, you could be off by 0.032 inches by final assembly. Remember, the specification for turret ring to hull interface was 0.004 inches maximum. The accumulated tolerances alone could put you 8 times beyond acceptable limit before you even started welding. Professional engineers knew about tolerance stack-up in theory. They designed for it on paper, but theory assumed tolerances distributed randomly across production. Some parts a little over spec, some a little under, everything averaging out statistically. Theory didn't account for the fact that metal from the same heat batch all responded to welding similarly, or that certain welders consistently ran their arcs slightly hotter than regulation, or that third shift working with older equipment produced parts with tolerances that skewed consistently toward one end. Then came the steel supplier variable that complicated everything further. Carnegie, Republic and Inland were producing armor plate to identical specifications on paper, rolled homogeneous armor, 0.475 inches thickness, Brinell hardness 230,000 psi. The Army inspectors tested every batch with standard procedures. It all passed inspection perfectly, but those specifications didn't control everything about the metal's behavior. Carbon content could vary between 0.38% and 0.42% and still meet specifications. Manganese could range from 0.70% to 0.90%. Chromium varied. Silicon varied. Each variation changed how the steel responded to heat in subtle but measurable ways. Carnegie steel running high on carbon content might distort 0.003 inches less than Republic steel running low on carbon. Same specification officially, completely different behavior under welding heat. Fisher Body No. 2 had actually tracked this correlation for 2 weeks in April out of desperation. Turrets built with Carnegie steel, 8.2% reject rate. Turrets built with Republic steel, 14.1% reject rate. Turrets built with Inland steel, 11.7% reject rate. The steel was all good steel that met Army specifications. It just wasn't identical steel in actual behavior. And in a production process with tolerances measured in thousandths of an inch, with 47 heat inputs distorting structure, with 23 separate components stacking their tolerances, not identical, became not acceptable for combat use. The real nightmare scenario that kept quality control awake, a turret built with Republic steel on third shift by a welder who ran hot, assembled from components that were all at the loose end of their tolerances by statistical chance. That turret would fight its hull every single time without exception. No amount of filing would fix it properly. You'd have to scrap it and start over completely, wasting all that labor and material. This was the reality Kowalski was up against with his idea. This is why the engineers with college degrees had given up on fixture-based solutions. Kowalski's design looked absolutely absurd on paper when he finally showed it. When he finally showed the sketch to his shift supervisor on July 14th, the supervisor actually laughed out loud. Not in a mean way, more like, "Walt, you've been working nights too long way." The conventional jig held the turret ring rigidly in place with 8 fixed clamping points welded solid. Bolt it down tight, weld it, unbolt it when done. Simple, predictable, wrong, but at least consistently wrong every time. Kowalski's design eliminated the fixed clamps entirely through a radical approach. Instead, he proposed using spring-loaded pins that would push against the turret ring from below, while allowing the ring to self-adjust during welding. The turret's own weight, roughly 1,400 pounds for the basket assembly, would press down on the springs naturally, but the springs would maintain constant upward pressure against that weight. As the welding heat distorted the metal in unpredictable ways, the springs would allow micro-movements. The turret ring would essentially find its own natural position, rather than being forced into one by rigid clamps. The supervisor's objection was immediate and obvious. "Walt, if it's not locked down solid, the whole thing's going to shift during welding. You'll end up with welds that are crooked, gaps that are uneven and wrong. It'll be worse than what we have now." Kowalski had thought about this exact objection for weeks. His design included 8 guide pins separate from the spring-loaded support pins that would prevent lateral movement. The turret could move vertically up and down, adjusting its height by a few thousandths of an inch as springs compressed or extended. But it couldn't slide sideways or rotate because the guide pins prevented that. The guide pins were loose enough vertically to allow the float tight enough laterally to maintain position. The really crazy part that made engineers' heads hurt, the final clamping sequence, was backwards. In the conventional jig, you locked everything down first with maximum force, then welded. Kowalski proposed the exact opposite approach. Weld first while floating, then lock down after. Let the turret float on its springs throughout the entire welding process without restriction. Only after the final weld had cooled for exactly 45 seconds would you engage the locking clamps. By then, the major distortion had already happened and settled. The turret had already adjusted itself to its natural position. The locking clamps would simply hold it in whatever position it had naturally settled into through physics. 2 engineers reviewed the design on July 19th after it got escalated. Both rejected it immediately with detailed explanations. The senior engineer, a man named Patterson who'd come from Buick's engineering department, wrote a 3-paragraph memo explaining precisely why it wouldn't work. The core argument, allowing the workpiece to move during welding, violates fundamental principles of fixture design. Movement during welding produces inconsistent weld penetration, creates potential for arc blow, and eliminates the repeatability necessary for mass production. Patterson was absolutely right according to every textbook, technically correct in theory. Every welding textbook ever written said the same thing. Lock the parts down solid, eliminate all movement, control every variable. But Patterson had never spent 19 years watching how metal actually behaves under industrial conditions in real factories. He'd never seen how a perfectly rigid fixture can fight against thermal expansion so hard that internal stresses crack the weld itself. He'd never noticed that the worst turret rejects weren't the ones that moved during welding. They were the ones that couldn't move, so they warped internally instead where you couldn't see it until final inspection. Kowalski went back to third shift without arguing. What would be the point of arguing with engineers? But he also couldn't let the idea go. On July 23rd, using his own time and materials from the scrap bin, he started building a prototype. Nothing fancy or expensive, just enough to prove the concept worked. He worked on it during his lunch breaks, 30 minutes at a time, in a corner of the jig shop where nobody paid much attention to what third shift was doing with scrap metal. The springs came from a batch of reject automotive suspension components. The guide pins he machined himself on an old lathe that was scheduled for maintenance. The base plate was scrap steel from a rejected hull section destined for salvage. Total material cost maybe $12. By August 2nd, he had something that looked like it might actually work in practice. Now he just needed a turret to test it on to prove the concept. Getting permission to test an unauthorized jig on actual production components was exactly as difficult as you'd expect. Kowalski asked his supervisor for permission. The supervisor said no immediately. Kowalski asked the night shift production manager next. Also no. He tried explaining the design to the quality control inspector who'd been at the plant since it opened. The inspector listened politely, and then said something about chain of command and authorized procedures that couldn't be violated. On August 9th, Kowalski got lucky through someone else's misfortune. A turret basket fresh off the welding line failed its initial inspection so badly it got tagged for immediate scrap. The measurements were catastrophic and beyond repair. The mounting surface was off by 0.019 inches on one side, 0.023 inches on the other. Normally this basket would sit in the scrap area for a week before getting hauled to the salvage yard for melting down. Kowalski asked if he could have it just to practice some welding techniques, he said casually. The supervisor shrugged without much interest. It's scrap anyway, do whatever you want with it. What Kowalski actually did was use it to test his jig design under real conditions. He cut off the original turret ring with a torch, cleaned up the mounting surface, and installed the basket onto his spring-loaded fixture. Then he tack-welded a replacement ring into position for testing. Not a good ring from production, just a salvaged one from another reject, but good enough to see if the concept worked. The basket floated on the springs exactly like he'd designed it to do. The guide pins kept it from shifting laterally as predicted. He completed the full weld sequence according to standard procedures, let everything cool per his 45-second rule, then engaged the locking clamps. When he measured the final result with precision gauges, the turret ring was flat to within 0.006 inches across its entire diameter. Not perfect by specification, but better than most of the good turrets coming off the regular production line. He showed the results to his supervisor the next night with the measurement sheets. The supervisor stared at the numbers in silence, then at Kowalski, then back at the numbers. Do it again. Kowalski did it again on a different reject. Same result within measurement error, third time with yet another scrap piece. Even better results. Right at the edge of specification, acceptable for production. By August 18th, word had spread through the plant among workers. The weird third shift jig that seemed to violate every fixture design principle was somehow producing better results than the engineering-approved equipment. The day shift supervisor came in early just to watch Kowalski demonstrate it in person. 2 welders from first shift stayed late to see it work with their own eyes. On August 23rd, someone made a critical mistake that changed everything. They sent a turret assembled on Kowalski's prototype jig through the regular inspection process without marking it as experimental. The inspector measured it according to standard procedures, stamped it approved with his certification, and sent it to final assembly. It mated with its hull perfectly with 0 gap visible. The assembly team didn't even realize anything unusual had happened until someone checked the routing sheet later and saw it came from third shift's experimental area. That's when the Army got involved in the situation. Captain Theodore Morrison from Army Ordnance was doing his monthly inspection tour of Detroit Tank Arsenal on August 31st. Someone mentioned the magic jig that third shift had built. Morrison was a mechanical engineer before the war, worked for Alice Chalmers in Milwaukee designing industrial machinery. He understood fixtures and tolerances. He asked to see it demonstrated immediately. Kowalski demonstrated the process twice under Morrison's observation. Morrison didn't say much during the demonstration. He just watched carefully, took notes, asked a few technical questions about spring rates and clamping pressures. When the second demonstration was finished and the measurements came back within spec, Morrison made a phone call to someone. 3 days later, 2 men in civilian clothes showed up at the plant with credentials from Army Ordnance Technical Division. They spent 4 hours examining Kowalski's jig, measuring every dimension, photographing it from multiple angles. They interviewed Kowalski for 90 minutes, asking detailed questions. Then they classified the entire design as restricted military information under wartime secrecy laws. The classification happened on September 7, 1943, with official paperwork. Kowalski's jig design was suddenly covered under the same secrecy protocols that governed tank armor formulas and fire control systems. He couldn't talk about it outside the plant to anyone. He couldn't write letters describing it to friends or family. Technically, he couldn't even tell his wife why he'd gotten a $50 war bond and a handshake from the plant manager as recognition. But the Army wasn't classifying it to bury it and forget about the innovation. They were classifying it to spread it systematically to every facility. Within a week, detailed engineering drawings of Kowalski's fixture, now formally designated self-aligning turret ring assembly jig Model K1, were being shipped under armed courier to every Sherman production facility in the country. Not suggestions or optional improvements, direct orders from Army Ordnance, implement immediately. Chrysler's Detroit tank arsenal went first since they already had the prototype. They built 11 production copies of the K1 jig in just 9 days. By September 20th, all 12 jigs were in service on the production line. The results showed up immediately in the inspection reports that were tracked weekly. Week of September 13th, reject rate 11.2%. Week of September 27th, reject rate 2.1% and falling. Fisher Body Plant, number 2, in Grand Blanc, received their drawings on September 15th by courier. Plant Superintendent Morrison, the same man who'd been staring at rejection tags 6 months earlier, assigned his best machinist and 4 helpers to build the jigs. They completed 8 units by September 28th, working around the clock. October's first week showed a reject rate of 3.4%, by mid-October 0.8%. Lima Locomotive Works in Ohio got their implementation done by October 1st, Pacific Car and Foundry in Washington by October 8th, Pressed Steel Car in Pennsylvania by October 12th on schedule. One by one across 8 states, the jig designs went into production at every facility. The training process was surprisingly simple, which helped rapid implementation. The K1 jig didn't require new skills or complex procedures that took weeks to learn. You set the turret basket on the spring-loaded pins. You positioned the turret ring. You welded using the exact same sequence as before. You waited 45 seconds after the final weld. You engaged the locking clamps. Done. Most welders got comfortable with it after 2 or 3 repetitions. What made the rollout possible was that every Sherman factory already had machinists who could build jigs from drawings. The K1 didn't require exotic materials or specialized equipment from suppliers. Springs, pins, steel plates, standard fasteners. Any decent machine shop could fabricate one in 3 to 5 days working steadily. Army Ordnance supplied the drawings and specifications. The plant supplied the labor and materials from existing stock. By October 31st, 1943, all 11 major Sherman production facilities had K-1 jigs in operation. The combined results exceeded even the Army's optimistic projections for improvement. Average reject rate before K-1 implementation, 12.3% across all facilities combined. Average reject rate by November 1st, 0.9%. The improvement freed up roughly 18,000 man-hours per month that had been going to rework. Those hours got redirected to building new tanks instead of fixing rejected ones, increasing overall output. The production numbers told the story better than any report. In August 1943, the 11 factories produced 1,947 accepted Sherman tanks total. In November 1943, 2,291 accepted tanks. That's 344 additional combat-ready Shermans in a single month, with no increase in raw materials, no additional workers, no expanded facilities, just less waste. The time savings per tank averaged 4.7 man-hours when fully calculated. That included elimination of most rework, reduction in inspection time, and fewer rejected units requiring complete disassembly. Multiply 4.7 hours by 2,291 tanks, and you get 10,768 hours saved in November alone. That's equivalent to adding 129 full-time workers without actually hiring anyone new or building more facilities. The Army Ordnance Department calculated that K-Twain jig implementation shortened Sherman production timelines by approximately 11 days per tank. When you factored in rework, elimination, and inspection streamlining across the entire process. 11 days times 2,000 tanks per month equals 22,000 tank days of production acceleration. Nobody told Kowalski any of this. He just kept working third shift, building jigs like always. Walter Kowalski never received a patent for his jig design, despite its massive impact. He couldn't under wartime regulations. Any invention developed using government materials, on government time, or related to military production automatically became property of the United States government. No patents, no royalties, no licensing fees, no recognition. He did get that $50 war bond as recognition. He also got his name in the plant newsletter, buried in the third paragraph of an article about production improvements. The article didn't explain what he'd invented or why it mattered to the war effort. Security protocols prevented that level of detail. It just said he'd contributed to improved manufacturing efficiency. In the larger historical record after the war, the K-form jig essentially vanished from memory. Post-war Army Ordnance reports mention improved Sherman production rates in late 1943, but attribute them to various process refinements without specifics about what those refinements were. The detailed engineering drawings remained classified until 1947, then got filed in an archive in Rock Island, Illinois. No dramatic announcements, no headlines in newspapers, just papers in boxes collecting dust. This wasn't unusual treatment for wartime innovations. Thousands of wartime manufacturing innovations followed this exact same pattern of obscurity. A worker at Republic Steel figured out how to heat-treat armor plate 12% faster, saving 4 hours per tank hull. Never got written up outside of internal memos that nobody reads. A machinist at Baldwin Locomotive redesigned the transmission mounting bracket to eliminate a persistent cracking problem. Saved countless field repairs on tanks in combat. Nobody knows his name today. A riveter at Pressed Steel Car, a woman named Dorothy Chen, developed a modified bucking bar technique. It reduced fuselage assembly time on B-24 bombers by 47 minutes per aircraft through better technique. Multiply that by 18,482 B-24s produced total, and you've eliminated 14,500 man-hours of labor. Chen's innovation got mentioned in exactly one document, a supervisor's log from March 1944. These weren't minor improvements that barely moved the needle. They were the difference between producing 2,000 tanks per month and producing 2,400 tanks. Between delivering 500 aircraft monthly and delivering 620. In aggregate across thousands of factories and millions of workers, these invisible innovations shortened the war. How much exactly? Impossible to calculate precisely, but historians have attempted estimates. If American war production in 1943-1944 had remained at early 1943 efficiency levels, before innovations like Kowalski's jig took effect, the timeline changes dramatically. The Normandy invasion would have been delayed by somewhere between 6 and 9 weeks due to insufficient armor support. Sicily might have been postponed significantly. The Italian campaign would have stretched longer with fewer tanks. Each week of delay meant more deaths, more destruction, more time for Germany to fortify positions or develop new weapons. The V-2 rocket program, the jet fighter development, the last-ditch defensive preparations in France. All of these benefited from time to develop. Anything that shortened the war measurably saved lives on both sides. Kowalski worked at Detroit Tank Arsenal until VJ Day in August 1945, when Japan surrendered. When the war ended, Chrysler shut down tank production within 3 weeks of the announcement. Kowalski got 2 weeks severance pay and a letter thanking him for his service to the war effort. He went back to commercial welding like before the war, spent another 18 years doing that, until he retired in 1963 at age 61. He died in 1971 at age 69 from natural causes. His obituary in the Detroit Free Press mentioned that he'd worked at the tank arsenal during the war. It didn't mention the jig or what it accomplished. His family didn't know the specifics of what he'd done during those years. The documents were still technically classified, though by then nobody cared much about Sherman tank manufacturing processes from a war that ended decades ago. But here's what actually matters about Walter Kowalski's story. Between September 1943 and May 1945, when the war in Europe ended, American factories produced roughly 31,000 additional Sherman tanks compared to what would have been possible at the pre-K1 efficiency rates with all those rejects. 31,000 tanks is not a small number. Some of them rolled onto Omaha Beach on D-Day. Some fought through the Ardennes during the Battle of the Bulge. Some pushed into Germany itself in the final months. Walter Kowalski built a jig on third shift using scrap materials, and that jig helped win the war.